Hello friends, I welcome you in lecture number 3 on sequence and series of complex numbers. In this lecture we are going to discuss about two important tests for convergence known as ratio test and root test. These tests are similar to the ratio and root test in real analysis. We are going to simply generalize them for the series of complex numbers. So let's start with ratio test. Suppose we are given some complex series denoted by sigma zn with non-zero terms. Sigma zn is a complex series such that zn is not equal to 0 for all n equal to 1 to infinity. Now suppose that limit of absolute value of zn plus 1 divided by zn is capital L. So here we are dividing with this zn, therefore we need this condition zn is non-zero for all n equal to 1 to infinity. So suppose this limit of ratio of n plus 1th term to the nth term is capital L. Then depending on the value of this limit capital L, there are three cases. So suppose L is less than 1, then given series is absolutely convergent, and hence it is convergent because we know that absolutely convergent series is convergent. If value of this limit capital L is greater than 1, given series is divergent, and if value of L is 1, this test fails and we cannot apply ratio test if this limit is equal to 1. So we consider one example. Check the convergence of this series sigma 20 plus 30i to the power n divided by n factorial. N is from 0 to infinity. For n equal to 0 we will have 0 factorial here, so it is 1. So each term of this complex series is non-zero. So this condition is satisfied. Sigma zn is complex series with zn not equal to 0 for every n belongs to n. So we first write the nth term of given series, which is zn equal to 20 plus 30i raised to n divided by n factorial. Here n starts from 0, 1, 2 and so on. Now we require ratio of n plus 1th term to the nth term. So first we find out n plus 1th term by replacing n by n plus 1 in this nth term. So therefore z suffix n plus 1 equal to, here we replace n by n plus 1 and here also. Now we find out absolute value of this ratio of n plus 1th term to the nth term. So we substitute values of zn plus 1 and zn is this, so 1 upon zn is n factorial divided by 20 plus 30i raised to n. Now this 20 plus 30i raised to n plus 1 can be written as 20 plus 30i raised to n divided 20 plus 30i raised to n plus 1 can be written as 20 plus 30i raised to n into 20 plus 30i. So this will cancel out with this 20 plus 30i raised to n, and we are left with 20 plus 30i and absolute value of 20 plus 30i. Similarly, this n plus 1 factorial can be written as n plus 1 into n factorial, so that will cancel out n factorial. So in this way, here we are left with n plus 1 and this will cancel out. So here we are left with absolute value of 20 plus 30i, and by the definition of absolute value, this absolute value is nothing but square root of real part square, that is 20, plus square root of square of imaginary part, which is 30. So this is nothing but 400 plus 900, which is square root of 1300 divided by n plus 1. Now we apply limit of this mod zn plus zn as n tends to infinity, which is nothing but limit of square root of 1300 divided by n plus 1, and limit of 1 upon n plus 1 is 0 as n tends to infinity. So we obtain that limit of absolute value of this ratio is strictly less than 1. Therefore, by ratio test, given series is convergent. So in this way, whenever we have this type of series in which we have this type of nth powers, it is easy to check the convergence using ratio test. We just have to find out limit of absolute value of ratio of n plus 1th term to the nth term. Another important test is root test. So suppose sigma zn is a given complex series with zn not equal to 0 for every n belongs to n. Now suppose limit of absolute value of nth term to the power 1 by n, or suppose limit of nth root of absolute value of zn is capital L, then depending on the limit of this depending on the value of this limit capital L, we have the same three cases as ratio test. If limit is less than 1, that is if value of capital L is less than 1, series is absolutely convergent and hence convergent. If value of limit is strictly greater than 1, series is divergent, and test fails if value of limit is 1. So here we are interested in the limit of nth root of absolute value of zn. Therefore this test is known as root test. So we consider one example of root test also. Check the convergence of this series whose nth term is given by n square I by 4 to the power n. So we try to find out this limit of nth root of absolute value of zn. So we put value of zn here, absolute value of n square I by 4 raised to n to the power 1 by n. So this is nothing but absolute value of mod n square raised to 1 by n and I by 4 raised to n raised to 1 by n. Okay, we will have this type of things, I by 4 to the n raised to 1 by n. This we can rewrite as absolute value of I by 4 raised to n into 1 by n. So we obtain absolute value of I by 4. Now this is independent of n, so we take it outside limit, and this is limit of absolute value of n square is n square because n is positive integer. So we take absolute value of n square equal to n square. This we rewrite as n to the power 1 by n whole square, and limit of square equal to square of limit of square of n raised to 1 by n equal to limit of n raised to 1 by n whole square, and this is standard limit. Value of this limit is 1. Also absolute value of I by 4 is absolute value of I divided by absolute value of 4, and absolute value of I is 1 and absolute value of 4 is 4. So here we obtain this limit to be 1 by 4 and it is strictly less than 1. Therefore by root test given series is convergent. So this is all about today's session. I hope you like this lecture. Thank you very much.